All right, looks like we have results from everybody. I'll have everybody unmute yourselves for me really quick. How do we feel about that quiz? All right. Are the Canvas quizzes working well? You guys are able to pull them up?
Yep.
When you were done, again, did it show you like which ones you got wrong or right or anything like that?
Yeah, it finishes at the end. It shows you which ones you got wrong.
Just which one you got wrong? Okay. Does it show you the correct answer? Or it just says you got it wrong?
Just says you got it wrong.
Okay, cool. All right, yeah, I'm just playing around with the settings and stuff, so kind of trying to treat it the same way I would if we were in class. All right, but just go through the results here and share the correct answers with you. The first, it might have shuffled the questions and answers for you, but what I've got on my screen, first one is why doesn't the moon fall towards the Earth? The correct answer is that the moon has what's called a high tangential velocity. We're going to talk about that today, but basically it's sort of falling sideways, so it's not ever going to hit the Earth because it's sort of falling around the Earth, which I know is a weird thing to think. Gravitational pulling from the sun maybe plays somewhat of a role, but not as significant as the tangential velocity does. So I can see how that threw some people off. But in terms of the, this is the kind of the law of one of Newton's conclusions, but every mass pulls on another mass with gravitational force that is, it should be directly proportional to their masses and inversely proportional to the square of the distance between them, which basically means you're making a fraction where the mass is on top and the distance is on the bottom. That's sort of it's kind of a confusing definition, but again, we'll look at that equation today. The inverse square law, put in simple terms, states that the greater the distance from Earth's center, the blank the gravitational force is, it is less. So the farther away you are from something, the weaker the gravitational force you're going to feel from it. You can think about this in real world examples. Think about astronauts, right? When they go from Earth's surface all the way up into the International Space Station, what's true about the gravity that the astronauts are experiencing? Yeah, it's a lot less. You've seen that they're floating around and stuff, and we often refer to them as weightless. But this is one of these things that if you don't take anything out of this unit on physics and gravity, I want you to understand that we do say they're weightless, but in reality, are they actually experiencing zero gravity? No. Is there such a thing as zero gravity?
No.
No, there isn't. There's always, you're just experiencing an extremely weakened form of it, but there's really, you're never out of gravity's influence. You're always being tugged on by something or by each other. It's just, it's so minute that eventually, our perception of weight is eradicated, but there's still gravity. Anyway, something we'll touch on again today. And finally, if two objects are placed far enough apart, the gravitational attraction, so this is exactly what we were getting at, will be zero. That is false. There is no such thing as zero gravity, even though we often say that term. So, all right, those are all things we're going to explore today, but it looks like you're feeling good about that from the reading. So that's encouraging to see. All right, our next task is to check out the voting form. Let me see here. I only have 7 responses. So does anyone still need to vote? Here, let me stop sharing really quickly. So how many people voted? Let's have a show of hands. Be honest.
Oh, no.
All right, so Will, I'm going to need you to go on Canvas and should be under assignments or announcements. Look for something with the voting form. I believe I made it a separate assignment. If you could go there real quick and cast your vote. Edward, were you able to vote? Yeah? All right. I haven't looked at the results yet, so if it's a tie, Will, it's going to come down to you, bud. You could be the deciding factor for $100,000. I don't know if anyone's read on the announcement too, but what's the prize going to be?
Extra credit.
It is extra credit. It's worth plus 5 points of lab points, and that's just going to be added to your grade overall. Or if you wanted to, I mean, you could add it to an assignment, but point is that it's just going to go into sort of your bucket of points. So let's see who comes out. Will, were you able to vote?
Yeah.
All right. I think maybe Grace, or no, yeah, we have 9 votes now. So Grace and Bryce maybe haven't been able to vote. I'll see if they end up making a deciding factor. But drum roll. Let me share my screen here. And let's check out the results. Holy moly. It was a 3-way tie between boiling seas, plastic pollution, and chemical pollution, but it looks like oil spills came out on top with 33.3%. So who did oil spills again?
Me and Will.
Nice. All right, Bear and Will, congratulations. You'll each get plus 5 points of extra credit. But good job and congratulations to everybody for your presentations. I know we kind of drew that whole project out for many more lessons than I initially planned, but I think it was sort of a helpful, slow transition into this online format. So, and hopefully, again, environmental stuff will continue to be a theme even as we move into our physics unit stuff. So, any other questions or comments on the project? Did you guys enjoy watching your Flipgrid videos? I haven't gone through them yet, but I'll go check them out. So I used to do a whole thing where you'd shoot each other with Nerf guns. I was going to try, hopefully that Flipgrid video was a somewhat similar time crunch thing. All right, our next task is number 3 right here on the screen. It is a formative assessment probe. These are those same little funny little worksheets that I used to give you that you'd fill out and I would collect. It's part of my graduate school research. Plus it's just a nice place to start these units off. I want to see how we're feeling about our understanding of gravity and gravitational forces. So please click on that. It should take you to a Google form that will look something like this. And I've actually literally just took a screenshot of the form itself, so please read over that text. And then I made form survey versions of the questions. So please take a few moments to answer those 2 questions, and then we'll come back to review it. Again, I will time us for about, let's say 3 minutes, but if I see that we've got 9 responses, then I'll bring us back together. And again, if you're not sure what to do or how to access this form, just chime in. I am still listening. 3 minutes, go for it. All right, looks like everyone has responded. So have you all unmute yourselves just so that I can, I still want to look at my screen, but I want to have some feedback from everybody too. So overall, who did you agree with, Ben or Kelly?
Kelly.
Kelly.
All right, let's see how we did. Looks like most of you went with Kelly. We have a small contingent that did hold out with Ben though, 2 people in particular. So that's a good thing. In terms of explanations, I mean, we kind of gave some of this away with the Do Now quiz as well as the reading, but this formative assessment probe is framed around the fact that all of us right now, you're familiar with gravity. We're experiencing gravity. You know that if you trip, you're going to fall. If you drop your pen, it's going to fall to the ground. And we are in the atmosphere. And we also know from movies and everything we've watched that once you get out of the atmosphere, right, once you're out in space, what's true about the gravity up there? What happens when an astronaut takes a pen, holds it, and then lets go?
Floats, there's less.
Floats.
It just floats, right? And we're like, oh man, it's like 0 gravity. Again, there's more going on there. There is actually still, gravity has just been reduced drastically, but technically is still present. However, you could still, like when they went and astronauts went and visited the moon, when they were walking around, were they experiencing gravity or were they still floating?
Experiencing gravity.
Yep, it's just a lot lower. Anyone ever watch that footage? It's kind of goofy looking where they're kind of like bouncing on the surface. And again, some people still claim that that's fake and they're on wires. But they were just experiencing a much lower form of gravity. So even on other planets that don't have an atmosphere like the moon can still experience gravity. And so again, we're going to be exploring more of that in this unit and chapter. So cool, thanks a lot for those results there. And that's, again, you might see questions similar to that on our next assessment. Okay, for task 4, I just wanted to give this a try of just sharing some slides with you and going over just really short kind of lecture like I would do in class. What I'll do is I'll pull the slides up here on the screen and just annotate. I just want to go through the 4 sections of the chapter really briefly that we did, and then we'll move on to a little activity, but I want to make sure we're feeling comfortable. So if you, you can, unmute yourself, or you can mute yourselves if you want, but if you have a question, if you want me to slow down or pause, feel free to chime in. And if you want to take notes on your a digital doc or on a piece of paper, you're welcome to do that. But if you took notes from the reading, I'm just going to be emphasizing stuff from the reading right And just to put that in context, so this is my first time ever teaching physics. This is one realm. I've taught biology, I've taught chemistry. I feel pretty confident in those realms. Physics, I took a lot of physics in college, but that was more than 10 years ago now. And so this is sort of a new realm, new area for me, which is going to be interesting. So bear with me as we go through some of this. So Isaac Newton is famous for what thing fell on him when he was sitting under the tree?
An
Apple.
Yes, right. And I always misunderstood this, myth. I always thought, okay, apple hit him on the head, and he's like, oh, it must have been pulled to earth by something. I didn't know that the true story is actually that he was comparing the apple to what?
The moon.
Yes, right. I didn't know that he was sort of like looking at the moon out there as well. Here's my little man in the moon here. It's not bad, huh? He kind of the real revelation of the story. I don't know if the story's true or not, but the point is that he had this idea that the same forces acting on the apple that dragged it towards the earth must also be acting on the moon, this giant piece of rock that is hundreds of thousands of miles away versus the apple, which was only a couple of meters above him. And so something had to be going on there. How do I go to the next slide if I'm annotating? I guess I have to exit annotations and then go to the next slide. Oh, and look at that, the animations stay on the screen. Sorry, so this is all, I'm playing with this here. So clearly what I have to do is clear those. All right, so you answered this on the Do Now quiz, but the reason that the moon does not fall directly to Earth like an apple is because the moon is doing what? What do they mean by tangential velocity?
It's going around.
Orbiting?
Yeah, it's got a sideways motion to it. And what's true about that sideways motion? What does it exceed or equal?
It like exceeds like Earth's gravity, so like it like goes around instead of being pulled down.
Yeah, so that's why I like this little kind of demonstration here, that if you pay attention to this side of the screen here, is everyone seeing the annotations I'm drawing on here? That if Earth were to suddenly disappear, right, then the moon would shoot off, kind of like releasing a rock from a sling, right? You know, if you were spinning a rock around a sling and then suddenly just kind of let it go, it's going to fly off in its own. The tangential velocity is what will take over, but the fact that gravity is pulling on the moon at the same time, it's keeping it in what we call an orbit, right? Where it is basically falling around our planet, which is kind of a weird way to think about it. But that's essentially what orbiting is. Earth is doing the same thing around the sun, right? The sun is pulling on Earth with a huge amount of gravitational force, but the Earth also has a very powerful tangential velocity that keeps it rotating around the sun rather than falling directly into it. That will change with time, right? Has anyone ever heard the term decaying orbit? Does anyone know what that means?
Is it where like the orbit like gets weaker?
Yeah, so eventually, right, over hundreds of thousands of years, it's kind of like a spiral, that things eventually get closer and closer. What's interesting about the moon, though, is, as far as I understand, and again, I don't fully understand it, is the moon actually eventually going to hit Earth? Like, is it going to fall into the Earth, or is it getting further away? Anyone know?
Further away, maybe?
As far as I understand, yeah, it's actually the moon is escaping Earth, that it's actually getting more and more distant, which is going to have interesting consequences for the oceans, because tides and things like that are very much governed by the movement of the moon around our planet. So I don't know what that's going to do, and it won't be in our lifetimes, that's for sure, but kind of an interesting thing to think about. Any questions so far on those first two chapters, Newton's thinking and tangential velocity? All right. Wow, this is really tedious if I really can't just go to the next slide here. Sorry, just trying to figure out how best to do this. So, all right. So I hate to say it, but if we're going to do physics, we're going to have to do a lot of what?
Math.
There's math. Oh boy, right? Everyone enjoys this stuff. So everything has gravitational force that pulls on everything else. I know it's weird to think, but even though all of us are in separate parts of the world right now, you are all still pulling on each other with a little bit of force. You could literally calculate it. And again, they give you this really confusing definition where they're basically saying that, right, it's directly proportional. Why did I suddenly lose my ability to draw? sorry, still trying to figure out exactly how all this, there we go. So this whole thing about how mass is directly proportional and the distance is inversely proportional, I know that's sort of confusing definition and terminology. So I think it's actually simpler to translate that into mathematical equation. And what they mean by the fact that mass is directly proportional to the force is, if you look at the fraction, where's the mass?
On top.
It's on top, right? That's the directly proportional, right? You're going to be multiplying force times mass if you were trying to solve for distance stuff. And inversely proportional to distance, it's on the bottom, right? We're always dividing by the square of the distance. I have no idea how they figured a lot of this stuff out. There is something missing from this. Did anyone read ahead? There was a section 5.5. Does anyone know what the next variable to be added to this equation is? There's a variable that's called g, and we're going to be adding that in, which is basically, it's called the gravitational constant, and it's just a really, really tiny number that brings things into reality, right? That because right now the way that they frame this, it makes it sound like, oh, like it makes it sound like I'm exerting a huge amount of force on everything around me. In reality, I'm not. I mean, there's definitely, I am pulling my computer towards myself by gravity, but you'll see by adding this variable g, it's a super, super small number, and it explains why the computer doesn't just get sucked towards my body like the magnet from Breaking Bad, right? Like it doesn't work that way. Gravity is actually pretty weak, and you need something that is like the size of a planet, like planet Earth, to really exert enough force to pull things towards it, which is why, again, things fall when we drop them because we're on such a huge planet. But when astronauts went to the moon, they experienced much lower amounts of gravity because the moon is a lot smaller and less dense. So kind of explains a lot of that, which I think is kind of interesting. So, all right. And finally, again, sticking more with the math, is this idea of the inverse square law, which is building on that same idea of how distance goes on the bottom of the fraction, right? That it's that same concept from the quiz that if you are, the farther apart objects are, the weaker the gravitational force between them. And that's because you're constantly dividing by, right, the distance squared, right? It's always the mass here was on top, and you'll see they've got the fractions going here, but it's always the distance, the square of the distance on the bottom. And so this is kind of a weird thing to think about, but I like this little demonstration here. They always use light to represent this. Here they're using the squares to represent the proportions, but if you were to suddenly, so take this as our reference point, right, R. If you were to move twice the distance, everyone with me that 2r means that you're twice as far away, what would then be the, what do they mean by the inverse square, right? If you're twice as far away, that means that the gravitational force is now, let's say the mass is 1, what would be the square of 2?
1/2.
Yeah, well, square of 2, if you add 2 times 2, would be 4, right? 2 times 2, that's the square. So the gravitational force, if you were twice as far away, would be 1/4, right? That would be the gravitational force. Does everyone see the fraction right there? 1/4?
Mm-hmm.
So there it is, right? What if you were 3 times the distance away? Then the gravitational force would be?
1/9.
1/9. Why is there 9 down there? What is 9 from?
3.
It's 3 squared, right? 3 times 3. So does everyone see what they're getting at with this idea of the inverse square? It just means that you're dividing by the square of the distance, right? So that's what that's getting at. And this we'll explore more by doing a little math. I know it's kind of, again, confusing with the units and things like that too, but kind of just a good place to start there. So, all right, so enough of me actually lecturing to you. What I want to move on to next now is kind of 2 kind of simplistic but fun little demonstrations that I actually found in the textbook. So we'll need our screens for this, and you'll need to watch me and what I do. It's all about perspective. We can explore this inverse square law, the fact that things reduce by the inverse square of the distance they are from us, right? And you can do this with your eyes. So what I want you to do, so I know it's a little weird, is hold one hand in front of your face, and then try to hold the other hand about twice that distance away, right? So you're going to have a bigger gap, right? You've got the distance from your face to your hand, And then the distance from one hand to the next hand should be about twice as far. Again, it's going to be kind of arbitrary. And so looking right now with two eyes, take a moment to unmute yourselves really quickly so that I can get some feedback from you as we're going. Looking with both eyes, do you see a significant difference in the size of your hands?
Yeah.
Maybe a little, but to me, it doesn't seem like that significant, right? So here's what we're going to change. Now, what I want you to make you do is try to bring your hands together so that they overlap a little bit, like maybe get your thumbs to overlap. And what I want you to do is only look through one eye. So close one eye. And what do you notice?
One's so much smaller.
See how the hand suddenly looks a lot smaller? In fact, if you kind of get the distance right, you could almost say that your hand that's further away is about 1/4 the size of the hand that's closer to you. Kind of play with the distance a little bit and see if you can get that to work.
That's
Kind of hard to
wacky.
hands, but it almost looks kind of cartoonish, doesn't it?
Mm-hmm.
Once you look with one eye, then it kind of really limits it, right? Our two eyes kind of throw that off. So again, if that wasn't working well for you, there's another way you can do it, and it involves money. What I need you to do is everybody take a few minutes right now to try to go get some dollar bills, or again, if you're, well, we're all here in the U.S., so see if you can go find $1 bills, or if you want to
Boys.
use $100 bills or Benjamins, you can use whatever you need to.
But
Go
use
try to find
the
$1 bills.
Zimbabwean money.
Oh yeah, if you got
100 trillion.
Oh hey, you got Zimbabwean dollars?
Oh yeah.
Oh man. Oh, I'm jealous
My
of that.
grandparents brought them back for all the children.
Oh, nice, cool.
Is plastic money gonna work?
Yeah, whatever it is. What the key is to have two things that are the same size. So that's the trick. So
I actually
whatever it
got
is,
2 coins right here.
if you've got Monopoly money, use that. Try to get two things that are the same size. That's the trick.
Oh, I got $1. That's it.
Oh,
And then
hey,
I got-
Chloe, high roller over there. Chloe's our high roller. Here we go.
All right.
All right. We are going to have to, we're not going to deface the money, but what you're going to do is, so we doing good here. Looks like let's wait on Cesar, Julia, and Will here to see if they rejoin us. But we're going to do another sort of perspective thing, and I think some of you kind of figured out what it is. But again, let's give them a minute to see if they come back. Julia, you got your move on?
I'll go zero.
When did you, so I lived in Zimbabwe for 8 years
Oh, nice. Wow.
when I was a little kid, but that's when my dad worked there as part of the UN. So that was before the economy totally tanked and they started making $1 million bills.
It's a $100 trillion note.
That is called inflation. So pretty
Inflation.
Those are like $5 too.
yeah.
I have a lot of $2 bills.
All right, Chloe's making it rain over there. All right, here's what we're gonna do. So one of the bills, what I need you to do is take one of them and just fold it in half, burrito style, right? So fold it in half like that. And then go ahead and fold it the other way, sort of the taco style, right? So that you end up with that. I promise you we're not making like a roll to snort cocaine or anything like that. Don't get so again, so you're folded across and then folded down so that it's, does everyone see how we're sort of like making a bill that is 1/4 the size? Does everyone see what we're getting at here? All right. So now we're going to do the same thing we did with our hands, but what you want to do is you want to hold the folded one closer to you, and then you want to try to hold the unfolded one as straight as you can. And again, looking with just one eye, try to put it far enough away that they end up being the same size. Again, keep them close to each other. And again, keep the unfolded bill. Does everyone see how you can eventually kind of find a spot where they're exactly the same size?
Yeah.
Isn't that crazy?
That is wacky.
And so that is what's called the inverse square law, right? Is that the farther away we see this bill, we are perceiving it as 1/4 the size, right? So it is twice as far away from our perspective as the folded one is. And so to our perception, it looks 1/4 the size that it actually is. And by comparing, right, we had a folded one that was exactly 1/4 that size and it ended up looking exactly the same. gravity works the same way, right? That if you're twice as far away from something, you're going to be experiencing exactly 1/4 of the gravity that it exerts on you. And so it's just hard to do that like in a room because we're talking about planet size, right? Like you've got to get a long way away from Earth in order to experience a lot less gravity, which is why astronauts have to go into space and get out of our atmosphere just to experience lower amounts of gravity. So making sense to people? Kind of a fun thing to do too. Will, were you able to do that?
Yeah.
Yep, cool. All right. The next thing we're gonna do is another activity, and we got 30 minutes. I'm kind of hoping we can at least get started on this, and you can kind of go do what you want from there. So, oh, did I close Canvas? No way. Oh, sorry, I'm in presentation mode still. So, all right. The next thing you're gonna do, the next task is gonna be sort of an away from your computer activity. You'll need to kind of follow the video, but then we'll resume class with about 10 minutes left. It's more of a hands-on thing. So this is number 5, exploring gravitational force. What I'd like you to do is there's a demonstration video that I've made through Swivel. If you click on this first link, it should take you to the Swivel site. The video will look like this, and you can play it. If that doesn't work for some reason, I also uploaded it to YouTube. So there's a link right below that. And you can actually, I think it's embedded. You could literally just play it right there in the announcement. But what I'm going to do is demonstrate 4 activities that I want you to try. You're going to need to be by a sink of some kind. You're going to need a cup, sort of a sharp knife or something like that. And you're going to need a book and a piece of paper. And I think you can hopefully find those things around your house. And if you can't, you can find substitutes. There's other things you can use. But the video will explain what you need to do. So I'll kind of give you about 20 minutes, I think, to kind of go off and do that. And whenever you're done, come back. And the link down here, there's a discussion that I've made on Canvas. It looks like this. So just go to our discussion. You should see Science2A Exploring Gravitational Force activity. And there are 4 questions that I'd like you to answer. So just hit reply, and you can start answering those questions. And it's okay if you don't get this done in like the 20 minutes, even if you only answer like 2 of the questions. If you hit post, it will save, right? It'll post your responses, and you can come back and edit it later. So don't think like you've got to like, oh, copy it out or whatever. You can always just post it and come back to finish it later on. You can always edit your posts. And if you can't, let me know, and we'll figure something else out, but that should work that way. So, all right, so I will leave you to it. Let's meet back here again in the main room at, let's see, class ends at 11:40. So let's meet at 11:30, okay? So at 11:30 a.m., just come back into the room. So you can leave the lesson to work on this. You can leave the Zoom room right now to work on this activity. I will still be here, keep it open. So I'm still here listening, so pop in if you've got a question or if something isn't working, and then pop back out again. But please plan on rejoining the meeting. We'll all come back together at 11:30. Clear on that? Go for it. How'd it work?
It went pretty well.
Yeah. So you're able to, did you watch the video through the Swivel thing or through YouTube?
Through Swivel.
Cool. Okay. Were you able to, what did you use? Did you use a cup or?
We had like these paper, I don't know, they almost look like ice cream bowls from like years ago that I just found in the garage.
Perfect. Okay. You able to find a book and stuff?
Yeah.
Cool.
Yep, a bunch.
Ed, what'd you use? I think you're muted, Ed.
Oh, I just used a paper cup that I had in my pantry.
Nice. How about you, Bear?
Found this metal cup in my trash can, so I use this thing.
Cool.
Were we supposed to film it or no?
Not like fill it completely, just with a little bit of water.
No, film it.
Oh, no. I had that idea, but I was like, there's no real point. Point was to make observations and then you can answer the questions. So yeah, nope. All right. Everyone able to find a container? All right. I think we just need to Will back. All right. Did that work out pretty well?
Yeah.
All right. Again, I'm going to try to do a mix of, there's plenty of online simulation stuff as well to use just through like FET and Edpuzzle and all that stuff. So I'll try to use some of that stuff too. But if I ever can, kind of in away from the computer, hands-on kind of thing, I'll explore those with household items, and we'll see if it starts getting more complicated and you can't find something, then we can, you can collaborate with somebody else who can find something. Anyway, but the point is to answer those questions on that Canvas discussion. That'll be the thing I'll check, but that will just roll into homework. So if you didn't get it done, it's okay. You can finish that up as a homework assignment. So on that note, the last task for today is homework, which is just to complete, make sure you make that discussion post, answer those 4 questions. I would like you, for Hewitt chapter 5, there are some reading check questions that I'd like you to do. They're on page 116 in Hewitt. So this is a digital version of the Hewitt book. So if you turn to the very end of chapter 5, and you'll see it's on page 116 here, it's listed somewhere, right there. Under reading check questions, I'd like you to answer the odds up to 7. So 1, 3, 5, and 7. 1 is what connection did Newton make between falling apple and the moon? 3 is in what sense does the moon fall? 5 is how does the force of gravity between 2 bodies change and the distance between them is doubled? Just getting at that math equation. And 7 is at what distance from Earth is the gravitational force on an object 0? It's kind of a trick question. So that's what I would like you to answer. Please type your answers into your digital notebooks. And then I can check them. What I'll probably do is create an assignment on Canvas that you can then just share your digital notebook with me. Just hit the share button on the Google Doc, and then I can easily go in and just look for and grade those questions. So just make sure you give it that title for the assignment. So, all right, any questions on what you need to do there for homework? The last thing, I keep forgetting to mention this, but if you have not done so already, there is a survey. It's just 3 questions. It's the very last thing on that post. It's Sci2A feedback about after 2 weeks of online learning. It is literally just 3 questions. It's just how are things going overall? What are some things that other teachers are doing that you'd like to see me do in our Science 2 class? And how are you feeling about how much computer time you have and whether we should prioritize online stuff or not? We've got 3 responses, so if everyone else who has not done that, please take a moment to do that as soon as you can. All right, so can I have you unmute yourselves, please? One last thing. So do people notice that when you drop the entire container, did anyone notice, did water dribble out of the bottom still?
No, it came out the top. Like, I was surprised too, because I dropped in my sink and it landed like smack dab upwards, and all the water came up on the top of my mirror, and I was like, bruh, I just got pranked by Mr. Hate. So I didn't think he was gonna do that.
Oh, I did. I warned in the video.
I remember. I was like, there's no way this all comes out of the top of here. And so I dropped it and it went everywhere, and I was like, bruh.
Yeah, well, that's one of Newton's laws, that for every action there's an equal and opposite reaction. So yeah, and that I did it to myself as well when I was first getting ready to film that. I made a mess in the sink. So, yeah, anyway, kind of fun stuff to explore. So we'll continue to do that. All right, kids, that is all I had for you. I hope you have a good rest of your day, and I will see you again on Thursday. Once again, if you got questions or anything for me in particular, just hang out in the room. But otherwise, we're all set. Have a good day. Thank you very much.
Thank you.
Thank you.
Thanks.